Hello everyone, welcome back to another video. In this video we start our exploration of Chapter 7, beginning with 7.1, which has to do with radical expressions and functions. So just to give an example of a radical expression, say we've got something like this. This is an example of a radical expression. It could be simplified because we've got the square root of 9 in there, so we can write this as, say, the square root of 9 times the square root of x. So we could simplify this to 3 square root of x, just for example. Now what we've just taken in this calculation is we've taken what's called the principal square root. So we've taken the principal square root, but what we're more interested in is, or not what we're more interested in necessarily, but what we can also consider is just the more general version of a square root. So for example, let's say that I'll type this just to go faster, find the 2 square roots of 16. Suppose that's what we're trying to figure out. I'll make this a little smaller. So we want to find the 2 square roots of 16. Well, we know the principal square root is 4. We know that 4 squared gives us 16. And then the other square root is negative 4. So 4 squared is 4 times 4, which is 16. And negative 4 squared, notice the use of parentheses, those are important. We get negative 4 times negative 4, which is also 16. So notice the difference. If we say something like find the 2 square roots, then we are talking about positive and negative solutions, not just positive ones. But if we say specifically we want the principal square root, then we only really consider the positive answer. So let's just take a look at some more examples. Let's suppose that we want to simplify the square root of 16 over 25. Well, whenever you're taking the square root of a fraction, you can basically just take the square root of the top and the square root of the bottom separately. These things are non-negative, so we don't have any issues with complex numbers or anything like that. So we just get 4 square root of 16 is 4, and the square root of 25 is 5. So we have evaluated the principal square root of 16 over 25, and we got 4 over 5. Now let's introduce some terminology. All of the things that we've looked at so far are called radical expressions, and then the thing under the radical is called a radicand. Just a way of referring to the thing under a radical. Okay. Next, let's take a look at the graph of the square root function. So I'll pull this down. We aren't too concerned with graphs in this class, but it's still good to know what it looks like, roughly. The square root function looks something like this. It's curvy, and it grows pretty slowly, is the idea. And you should have a point at, like, say, 1, 1, because the square root of 1 is 1. And you should have another point, say, at 4. It should give you 2, because the square root of 4 is 2. So this is just kind of a rough sketch, but notice that the domain, let me label this a little better. This is y equals the square root of x. Notice the domain of this function is only the non-negative real numbers. So we have 0 and all of the positive real numbers. So that's just a quick sketch of the square root of x. With that in mind, let's tackle another example. Let's suppose that we're given the following function. Suppose we're given f of x is equal to the square root of 5x minus 3. Now suppose we want to evaluate f of 1, just for example. We would plug in 1, and we would get the square root of 5 times 1 minus 3. We work within the square root, and we get the square root of 5 minus 3, which is just the square root of 2. And you could approximate this if you want, but usually we just leave things as exact answers. So that's how we can evaluate a square root function. And now let's take a look at something a little bit different. Let's consider, let me map or pan out a little bit. Let us consider, make this a little bigger too. Let's consider simplifying something of the form the square root of a squared. Well, let's just consider a few examples. Let's consider, say, the square root of 5 squared. Well, in this case, we can really just think about the square root and the square canceling, because we're talking about the square root of something positive. So we ultimately just get our answer as 5. What about the square root of 0 squared? Now, because 0 is non-negative, we can just basically cancel out the square and the square root. We just get 0 again. But now let's consider something a little different. Let's suppose we've got the square root of negative 5 squared. Now, we don't just cancel out the square and the square root in this case, because we're taking the square root of a negative number squared. So let's just think about this in steps. If we evaluate, so maybe I'll make a note first. This does not equal negative 5. So that was my point a second ago. This does not equal negative 5. You can't just cancel out the square and the square root. But it does equal, let's think, we take the square root, we simplify negative 5 squared, we get 25. And we know that this is just the same thing as the square root of 5 squared, or this is just the same thing as positive 5. So note that whenever you take the square root of something, you've got to get a positive number. When you take the square root of something squared, that is, you have to get a positive number. Okay. Another way to kind of shorthand what we've got here is just to say that the square root of a squared is just the absolute value of a. Remember, the absolute value of a just takes the thing that's squared and it makes it, it just takes, say, negative 5 and it just made it positive in our case. So the square root of negative 5 squared is, say, or maybe I'll use a different number just for variety. The square root of negative 3 squared is the same thing as the absolute value of negative 3 from this. So this is just 3. Okay. Let's pan out. Let's take a look at some more examples. It's always a good way to learn math, is by examples. Let's simplify some radical expressions, and let's assume that the variable that we're taking the radical of can represent any real number. So what about the square root of 36t squared? So we're assuming that the variable can represent any real number. So it's not just necessarily positive things, in other words. So what we do is we apply the same rule we just learned. The square root of something squared is just the absolute value of a. So we just really need to rewrite this so we can recognize it as a square. So I can say this is the same thing as the square root of 6t all squared. And now we just use that rule. This is the absolute value of the thing that you're squaring. That's the rule above. It's the absolute value of a. And in our case, a is 6t. So we just got the absolute value of 6t. And if we want, we can actually write this as 6 times the absolute value of t. We can pull out positive numbers, or I suppose we can pull out any real number out of the absolute value in this way whenever we'd like. So maybe just for brevity, just to negative 9t, the absolute value of negative 9t is the same thing as 9 times the absolute value of t. You can check that with some values if you'd like. So we've covered a good variety of examples, and in these examples we've supposed that the thing that we're taking the square root of can represent any real number, but we can make an assumption, in other problems they may make an assumption that the expressions being squared are non-negative. So we don't have to worry about the whole absolute value notation in that case. So maybe I'll actually type up this example. It's example 6 in the book. I'll type it really quick what it says. So it says, make this bigger. I think I'm getting a little bit too big in my text, but anyway, I think I zoomed out too much. Let's make this more, make this better size. Okay, here we go, exercise 6. Now exercise 6 says, simplify each expression. So the same kind of thing we've already been doing. Assume that the expressions being squared are non-negative. Thus, absolute value notation is not necessary. I suppose I need a hyphen here. Okay. So assume that the expressions being squared are non-negative, thus absolute value notation is not necessary. So, for example, say we want the square root of y squared. Y is assumed to be non-negative, so we just get y as our answer. Consider another. What about the square root of a to the 10th? Well, notice that we can write the square root of a to the 10th as a to the 5th, all squared. And we can just cancel out the square and the square root because of our assumption that the expressions being squared are non-negative, so we can just get a to the 5th. So it's much nicer in that case. Lastly, let's consider square root of 9x squared minus 6x plus 1. Let's think about how we can express this as a perfect square. Well, if you think about it as a perfect square trinomial, this turns out to just be 3x minus 1 quantity squared. 3x squared gives you 9x squared, negative 1 squared gives you positive 1, and then if you take 2 times 3x times negative 1, you do get minus 6x. So this checks out. It is a perfect square trinomial. And again, because we're assuming that the expressions being squared, we're assuming 3x minus 1 is non-negative, we can just simplify this as 3x minus 1. We can just cancel out the square and the square root. Okay, next, let's talk about cube roots. So we've already talked about square roots. Let's take a look at everything we've done so far. Quite a bit. You can see I started magnifying the drawings a little bit too much relative to the title, but that's okay. So let's pull this to the side and let's talk about cube roots. So for cube roots, let's just look at an example right away. Let's say we want to take the cube root. Notice now we put this 3 there. And I'll point out that in our square root notation, there really is like a 2 right here in each of these square roots, but we usually just don't write it. So I won't write it just to follow convention, but just know that's really what that means. It means that that's called the index of our radical. So the index is right here. It's the 2 that we don't usually write. And then the index of this radical is 3. But anyway, jumping back to our example, let's consider the cube root of, how about 8x cubed? Cube roots are nice. Cube roots, because we have an odd index, we don't have any of the absolute value business that we had when we were talking about squares and squaring things. So here's what we get in this case. We take the cube root of 8, we take the cube root of x cubed. We can split things up this way if we'd like. Or, better yet, instead of splitting things up, maybe we don't know about splitting things up yet, we can write it in this form. 8x cubed is the same thing as 2x quantity cubed. And very nicely, just like when we assumed, when we were working with squares down here, when we assumed that the expressions being squared are non-negative, just like in that case, when you're taking the cube root of something, you can really just cancel things out like you would expect. You can just get 2x. You just get the cube root of something cubed is just that thing. It's just 2x. The graph for the cube root of x is very similar. I will pass on graphing that for this video, but note that it's very similar. It just grows a little bit more slowly. You still got the point at 1, 1, but then, as we just saw, the cube root of 8 is 2. So we would have to go out all the way out to 8 before we would get up to 2 on our graph. But we don't care about graphs too much in this class, so I'll put that aside for now. But let's look at some more examples. Let's suppose, let me zoom in. Let's suppose that we want to take the cube root of actually, sorry, I want to rewrite this a little bit. Let's suppose that we have the function f of x is equal to the cube root of x. And suppose they want us to evaluate f of 27. That means to plug in 27 in for x into our function, so we get the cube root of 27. But notice something special about the number 27. The number 27 is just the same thing as 3 cubed. So we've just expressed 27 as a perfect cube, so we can in effect cancel out the cube and the cube root and just get 3. So f of 27, when we plug in 27 into our function, we do get 3. So f of 27 is 3. So again, just to emphasize, this is an odd root. When you're taking odd roots, it's much nicer than when you're taking even roots. When you're taking even roots, you have to, unless the problem specifies that the things you're dealing with are non-negative, you do need the absolute value notation. Let's take a look at one more example. Let's suppose that we are given something a little bit more exotic. Let's suppose we're given the function g of x. So maybe new example. Suppose we're given the function g of x is equal to the 6th root, just why not, you know, the 6th root of 7 minus 3x. So we want to try to determine the domain, find the domain of this function. Well, this is something we talked about, I believe it was in chapter, it was in between chapter 4 and 5. We were talking about the domain of the square root function. And it turns out that the same idea applies here when you're talking about any even index. So here the index is 6, that's an even number. So when you're talking about the domain of an even index radical, you can always just take the thing that you can take the radicand, using that terminology we learned earlier. The radicand is the thing under the radical. You take the radicand and you solve for where it is greater than or equal to 0. So this is exactly analogous to when we were working with square roots. It just turns out to be the case that it's true for any even index. Any positive even index, I should say. But anyway, we get 7 is greater than or equal to 3x after adding 3x to both sides. And then after dividing by 3, we just have 7/3 is greater than or equal to x. Or in other words, x is less than or equal to 7/3. So that's the domain. If you want to be fancy, you can say come up here and write it as every real number less than or equal to 7/3. So using interval notation, that would be this. Because our number line, we've got 7/3 right here, and it's every number to the left of it. So that's our domain. Alright, so that's the end of this video. I just wanted to create a video on section 7.1 before our next lecture. Zoom out and just see all that we've done. It seems like a lot, but it's not too much. So in the next video, we're going to jump into section 7.2. Please leave any comments if you have any questions, but I will see you all in the next video.